All right, thank you very much for everyone joining. So today we have another session of our quantum error correction tutorials. And just like last session, again, Kishor will present to us. And this time he will talk about our quantum LDPC codes. So Kishor, the floor is yours.
Yeah, okay. Yeah, thanks, Toby. Okay, so we will talk about LDPC codes, basically quantum low density parity check codes. And before we talk about LDPC codes, let's first understand, what are, before we understand what is quantum LDPC codes, let's try to understand low density parity check codes. Okay. So the goal is reliable communication over a noisy channel. And for that, what we do is this thing called error correction. And for error correction, you have a parity check matrix, basically. So that we know, like from previous discussions. And the code word is something which is in the kernel of the matrix, this parity check matrix. So if your parity check matrix is sparse, then that's what people mean by low density. So if your parity check matrix is low density, then it's called a low density parity check code because the parity check matrix is low density. And that basically means that this parity check matrix is sparse. So normally, let's say your parity check matrix had, like m rows, n columns. And if the number of ones that you have is much smaller than m cross n, then you will call it, a low density parity check code. So the number of ones divided by m cross n, that should be much smaller than 1. If that is the case, then you have a LDPC code. So LDPC codes, basically, one can say that the number of bits which are involved in each check and the number of checks acting on each bit are bound by a constant for all members of the code family. So there is a code family for which you can, you can talk about different parity check matrices. And for every parity check matrix, you can say that, the row sparsity and the column sparsity is basically bounded by a constant. And this is a very important code, and it's very much used in Wi-Fi, DVB-T, 5G, like even in space communication and so on, like how satellites communicate. Like at all these places, LDPC codes are used a lot. Okay, so that's good. And LDPC codes has gained lots of interest in the quantum world after this very nice paper by Daniel Gottsman. I will talk about all that, like later. So let's first try to understand, like a brief history of LDPC codes. So in 1948, Shannon published his famous paper on capacity of channels with noise. So that was the 1948 famous paper. And then 15 years after that, Robert Gallagher, he writes his PhD thesis on low density parity check codes. So that was 1963. He introduced LDPC code. He analyzes them and gives some decoding algorithms. But at that time, the computers were not powerful. So the computers at that time, sorry, just a minute. So the computers at that time were not powerful. So he could not verify that his codes could approach capacity. So this is something interesting, right? I mean, you see that the theory was developed, and also the decoding algorithms were not that good. So for almost 2 decades, people did not focus much on the Gallagher's LDPC codes. Then in 1982, Tanner, basically, he considered Gallagher's LDPC code, and he basically he introduced this notion of something called a Tanner graph, which is used a lot, to talk about which parity, like which bits you want to measure the parity for. You see that, even in the quantum case, we have this quantum Tanner graph and so on. So it goes back to 1982 when, like, Michael Tanner, he introduced this Tanner graph basically. But still you see that, like LDPC codes are not like, popular. And then 1993, a very nice code called Turbo code was introduced, and they exceeded the performance of all known codes and had low decoding complexity. And by 1993, 1995, people start getting interested in Gallagher's LDPC code, and like many people like David Mackey and others like start working, and they popularized LDPC code. So you see that it almost like it's 32 years. Like it takes 32 years from the birth of LDPC code to like it's getting popular, to the point that like currently, like in Wi-Fi and space communication and everywhere, people are very much interested in LDPC codes. Yeah. So today LDPC codes are ubiquitous, like they are used in Wi-Fi, 5G satellite communication, and so on. Like they are very popular. Okay. So quantum LDPC codes are basically quantum analog of LDPC codes. And basically a quantum LDPC code is a stabilizer code whose generators have the following two properties. So these are the two properties. Each generator acts on only a constant number of qubit, and each qubit is involved non-trivially in a constant number of generators. So every check acts on constant number of qubit, and every qubit is involved in constant number of checks. And when we say constant, it means for a family of codes. So you increase n, and as you go in higher and higher, like code, like in your code family, basically your the number of qubits which are involved for a generator, and number of generators that act on a qubit, like they are some fixed constant. So for example, you can think of Tori code, they are like it's always 4, that the constant is 4. You can go for very large size and it does not matter. Okay. And these codes, they can remove the polylogarithmic overhead that we normally have in the threshold theorem, which I will discuss next week. And in this paper by Daniel Gottsman, Opportunity and Challenges in Fault-Tolerant Quantum Computation, basically Daniel Gottsman talks about that a lot. Okay. So here is a more rigorous definition, like I have like added, of quantum LDPC code, where it says that an NK stabilizer code is an RC LDPC code if there exists a choice of generators for the stabilizer Q, such that weight of each of the generator is upper bounded by R for all I, and number of generator which act non-trivially on qubit J is at most C. So these two parameters R and C, they define this RC quantum LDPC code. Okay. And you can show that, like every stabilizer code is automatically an an LDPC code for large value of R and C. But normally when we are talking about LDPC code, we assume this R and C to be constant. So it should not scale with n. But obviously, if you make it a function of n, then every code is an LDPC code. But normally you want this R and C to be a constant. Okay. So LDPC codes, like, so basically Daniel Gottsman wrote a very powerful paper, and he suggested that, so this was a very powerful for 2014, where he shows that I saw that in the asymptotic limit of large circuit, the ratio of physical qubit to logical qubit can be a constant. And this was interesting because earlier people were talking about this ratio will be polylogarithmic. And he said this can be made constant. So that's what the paper was about, like fault-tolerant quantum computation with constant overhead. But the codes for which this can be done was not very much available. And people started developing codes which have, good parameters. So I will explain what do I mean by good parameters, or what are the good codes. So people try to develop better and better codes which are like, better encoding rate and better distance, so like over time. So there is this paper like by Brookman and Nicholas Eberhardt, where they try to develop better and better code, but somehow this is also not enough, like, I mean, like this kind of K and D behavior. And for that, what we actually need to achieve very nice performance is something called a good quantum LDPC code. So many of you might have heard about this word, like good quantum LDPC codes. So a family of quantum LDPC codes is considered good if they simultaneously achieve two things. One is constant rate, like this encoding rate that should be, like a fixed constant, as, like let's say n goes to infinity. And the distance should also go linearly, which means the distance by n should also be a fixed constant. So you see that we want both the encoding rate and the distance to grow linearly. And here we don't have both of them growing linearly. So that's why, like these are not enough. These are not good LDPC codes. Yeah. Now what happens that in the classical setting, getting good LDPC code was like very easy. Like you take a random, like parity check matrix, uh, and that has, like good parameters, like they have linear distance and linear encoding rate. But if you remember, in what happened that for the CSS code, let's say, for example, if you take two classical check matrices, let's say HX and HZ, and even if they can be, like you can take them randomly, and they can have they can correspond to good parameters, but then the issue is that HX HZ transpose equal to 0 may not be satisfied, which is a CSS condition. And that has been, like stopping people from developing this good quantum LDPC code for a long time. So basically, what we want is that the encoding rate should scale linearly with n, and the distance should scale linearly with only n. But if you recall from the last session, we discussed this thing called Brabby-Pollin-Terhal bound, which says that encoding rate times distance divided by 2 by d minus 1 should scale, like, should be order n. So if you take k equal to Rn, d equal to delta n, so let's take capital D equal to 2 in for a two-dimensional lattice, kd squared will be kd squared will be order n cube actually. Yeah. This will be order n cube. Order n cube. And this order n cube is much larger than order n, which is allowed by the Brabby-Pollin-Terhal bound. So it means that you have to violate the assumption of BPT bound, which assumes that, like you have the codes, I mean the parity checks, like in the way they are acting, it's like it's geometrically local. So good quantum LDPC code need non-local interaction. That's the message. So using non-local interactions only, you can achieve good parameters. And indeed, in 2020, after 2020, like 3 such codes were, I mean, and more, maybe one more code was developed which achieved these parameters, like, all of them, like, the encoding rate and the distance basically, like scale linearly. So somebody can ask, sure, I mean, you need non-locality, but how much non-locality is needed? Like this is an important question that somebody can ask. And for a long time, that was also an open question until, like Dai and Lee basically showed that if you want above the BPT bound, any 2D embedding must have at least this many number of interactions, like non-local interactions of length this much to achieve a particular nk d value, where hash star is the value here, like max of kd, and l star is this number here. Yeah, and what they showed, this is also asymptotically optimal. So if you want a particular nk and d, I mean, if it satisfies the Brabby-Pollin-Terhal bound, then everything is fine, life is good. But let's say if you want to go beyond Brabby-Pollin-Terhal bound, then you need these many non-local interactions of length this much to achieve those parameters. So this is something to keep in mind. Okay, so I hope, like, I mean, all this thing like makes sense so far. I mean, if you have any question, you can ask, or else, like I proceed with this hypergraph product construction, a particular quantum LDPC construction. Okay. So a particular construction by Tillich and Zemmour is called this hypergraph product code. And in here, basically they managed to, like have a constant rate, constant, like, like asymptotically, like k by n, basically they could get constant. And they proved that the minimum distance grows proportionally to a square root of the block length, which is basically n. And this was something interesting, because what they showed that you can start with two classical codes with parameters nkd, n1, k1, d1, and n2, k2, d2, and you can use their construction to construct a CSS code whose parity check matrix X matrix is given by this, Z matrix is given by this, and the parameters are basically given as this. So let's take, like a n1 equal to n2 equal to n. So this will go like n square, k1, k2 plus k1, k2, k1 transpose, k2 transpose. I mean, that can also like go like n square. But this one will go like, even if you take like good LDPC code, kind of, like HX and HZ, it will go like, like n. And so basically, if you take n square, you scale that and call n prime, then this will be like square root n. So there was this square root n barrier, which, I mean, was difficult to break. Like with hypergraph product code, you can get like square root n. So you can get like linear encoding rate, and you can, but the distance that you get squares like goes like a square root n in this case. And you can understand this hypergraph product code via chain complex language also. So if some of you remember, like, I mean, we talked about this topology and so on, like, I mean, I think first or 2-3 sessions, you can think of the hypergraph product code as tensor product of, small length chain complexes. So let's say you have a chain complex, and let's say this aj is a vector space over, let's say, fq, and you have some boundary operator delta j, which takes you from aj to aj minus 1, such that delta j plus 1 equal to 0, which is the fundamental lemma of homology, and which is what you need to construct a chain complex. If you recall that, like we have this homology group, which is like kernel of delta j by, even like, I mean, this quotient group, which we call like the jth homology group, for example. And you can take two such chain complexes, and you can make a tensor complex where the kth, like object of length size k, that is basically ai tensor bj such that I plus j equal to k, and you take direct sum over such objects, and you call that ck. And you can define appropriate boundary operator such that it satisfies the fundamental lemma of homology. And the way you define it has to satisfy something called Cauchy sign rule if you are working with FQ. But if you're working with F2, minus 1 is equal to 1, so you don't need to worry about it. It's all fine. So what you do is that you take your classical code, which is basically a length 2 chain complex. And here this delta C represents H. And what you do is that you take two such chain complexes, and from that you build, the tensor product chain complex. And you use the Cauchy sign rule to construct the boundary operators, which give you, the appropriate parity check matrices. Yeah. Okay. So that's why you have, like this kind of structure, like H tensor identity tensor H, and so on. Yeah. Anyway, so hypergraph product code, I mean, I just discussed that, you can take two classical code, and that can give you a hypergraph product code, but like the it has this square root n barrier, like, I mean, that it managed to go beyond square root n, but breaking that barrier was difficult. So a very nice intuition. So I'm taking this, like from some Simon's talk. So to go beyond the square root n distance, one has to not take like a regular product, but like you have to bring some kind of a twist. And if you think that like let's say the distance basically on a torus is the size of the shortest non-trivial loop, but if you do a twist, then the size basically of the shortest non-trivial loop can increase. So if you cut open and twist the torus, then you can increase the distance. And using this kind of like twisted products and so on, like more complicated product constructions, people manage to like get basically uh, this good quantum LDPC codes. So that was a breakthrough development. I mean, I think the first it was done by Pantalev and Kalachev, and then I think several people after that, did it. So this was a breakthrough. What like okay. So now once this codes were like developed, it led to breakthroughs in other areas also. And one such example is this quantum NLTS conjecture. So this conjecture was resolved by uh, Anurag Anshu, Chinmay Nirke, and Nicholas Brookman. So this conjecture is related to something more profound, which is called quantum PCP conjecture. So this is still a conjecture. I mean, like it's arguably one of the like toughest problem in quantum complexity theory. I mean, so far. So what is a quantum PCP conjecture? So what it says that there is a family Hn, alpha n, beta n, parameterized by n of Hamiltonians, such that beta n minus alpha n is, let's say, constant. And h that you have here is local with polynomially many terms. So it's like it's scale of local, so some fixed constant. Now deciding if ground state of Hn is less than alpha n or greater than equal to beta n is QMA hard. So normally, let's say if alpha n minus beta n is basically 1 by poly, then we know that like this is QMA hard, like that's due to Kitaev and others. But let's say if you make this gap constant, even after that, deciding if the ground energy is, let's say, above beta n or below beta alpha n, given that the gap between beta and alpha is a constant, which means does not depend on n, is still a QMA hard, is something which is like people have not managed to prove. But what happens that it implies something which is called NLTS. So NLTS basically what it says. I mean, so yeah. So NLTS. I mean there is something else that maybe like I should talk about later. So this is the NLTS theorem because people managed to prove it, and maybe once I mention what they did, then it's better to understand that. So what they say that there exists local Hamilton. So what is NLTS? NL is like no, and this L is low energy, and T is trivial, and S is states. So you have the ground energy, and there are states near the ground energy which are called low energy, and no low energy trivial state means that there exists Hamiltonian for which none of the low energy states are trivial states. And one of the definitions of triviality that they could think, I mean, they thought proposed, I mean, by I think Friedman and Hastings, was that you cannot represent that using constant depth circuits. So there does not exist Hamiltonians. So yeah, so there exists. So basically, the conjecture was that there exists Hamiltonian such that like none of its low energy states are basically trivial. Like you cannot represent them using constant depth circuit. This was important because assuming assuming this plus something like interesting. So So let's say if NLTS conjecture was false and quantum PCP conjecture is true, then NP is equal to QMA. So this was a kind of a tussle. But what people managed to show that this NLTS, conjecture is actually true. And to prove it, the Hamiltonian that they constructed was the Hamiltonian from the good quantum LDPC codes. So that was the breakthrough thing. It's a very short paper, and they take, given any, a CSS code or it's a stabilizer code, you can construct a Hamiltonian. And what they showed that, I have a formal statement. Yeah. So they showed this thing. They showed that there exists epsilon greater than 0 and a Hamiltonian family Hn such that every state psi of energy less than equal to epsilon n. So these are the low energy states. The minimum depth circuit to generate psi is omega log n. So you need at least log n depth circuit to generate them, which means they are not trivial. They are non-trivial. Okay. So this was the, breakthrough is work. And the good LDPC codes provide such NLTS local Hamiltonians. So people did not know example of such Hamiltonians for which this happens. And basically, yeah, the construction of good quantum LDPC code led to this interesting work in complexity theory. Okay. So that's it. I think now I will just talk about the final part, which is this IBM's bivariate bicycle code, which is so. So far we have been talking about asymptotically and so on, but there is a famous saying that asymptotically we are all dead, and maybe we should care for a particular n and can we develop codes which are, let's say, correspond to, I don't know, take n equal to 1,000 or n equal to 300 or 200, and corresponding to that, can you develop LDPC codes which have better parameters than what we have for, let's say, surface codes, better distance, better encoding rate, and so on. And in fact, there was a very nice paper by IBM team, and there was a quantum magazine covering up that also. It says that this could make quantum computing 10 times more efficient. Yeah. So there are some very nice codes that they proposed, which these are the parameters. You can see, and yeah, very very nice encoding rate, very nice circuit level distance, and so on. And to construct these codes, which are basically CSS codes, you see that you need two variables. So it's there are two variables x and y. So that's why these are called bivariate bicycle code. And bicycle because the parity check matrix has this two block structure. There's a matrix, there's another matrix. They are they have the two block structure. So that's why it was called bivariate bicycle code. And to construct this matrix A and B in your parity check matrices, you basically you build some polynomial. So you have, let's say, this A is some polynomial with, let's say, 3 terms. B is a polynomial with, let's say, 3 terms. And this polynomial could be x cubed plus y squared. The polynomial for B could be, for example, this one. And what are these x and y? X and y are some shift matrices which are defined here. So using this, you can define these parity check matrices. And they had a very nice statement that this is how you can calculate your n, k, and d. So the job is to just find better and better polynomials for which you can find a nice encoding rate and distance. And yeah, in fact, there are many such polynomials for which they had this distance. And one can ask, can one optimize for n, k, and d? Can one reduce the weight to check operators? And in fact, with Tobias and others, we extended this to multivariate bicycle code, and we got some nice code such as 34.5 code, and so on. And yeah, Lucas and Seaman, others were involved. And then there are other extension also which are trivariate bicycle codes. So I think that's it. People have any question, they can ask, or else. Thanks for listening. Yeah. Yeah, I mean, just unmute and ask. Yeah.
Yeah, if there's any question, just ask. No, I think there's a question by Shushtant. Can you unmute yourself?
Hi. Hello.
Yeah.
Okay, hi. So in that screenshot that you have, it says quasi-cyclic. Can you expand on that a bit? Like, what does this quasi-cyclic mean? No, at the end, this one, quasi-cyclic quantum LDPC codes.
Yeah. So normally cyclic code has this structure, right? I mean, so cyclic code does not have this two block structure. So this
Okay.
is like cyclic, but not exactly cyclic. It's bicyclic. Yeah.
Okay, so only to it's cyclic only to a certain degree, kind of.
I don't know, like, I mean, what is the, I mean, I haven't seen exact definition, like what they mean by that, but it's like there is a bicycle structure and there are like two variables. So it's called bivariate bicycle code. Yeah.
Okay.
But it's not a cyclic code, but it's almost cyclic. So you can call it quasi-cyclic. But I don't know whether there's a quantification or not. I mean, that I'm not sure about.
Okay. Thank you.
Maybe just this question. So when you talk about LDPC codes, right, you mean they only act on a few qubits, right, or a constant number of qubits?
Yeah.
But in a classic sense, this only involves, like, say, doesn't involve any geometric notion, right? It just says like there's this many bits or variables in the active, right? But like in the quantum case, I think we also may want to have some geometric notion, right? I mean, of course, it depends on the platform you have, but I'm not sure this is usually not enforced in LDPC, right? Let's say in the good LDPC codes.
So LDPC, even in the quantum case, they can be, so your checks can act non-locally, like even in the quantum case. The only constraint is that every qubit should participate in constant number of checks, and every check should act on constant number of qubit. But the checks, so given a check, the qubit on which it acts, those qubits can be geometrically non-local. But yeah, so I mean, in fact, that's what you need. So that's what this Dai paper was about. That yeah, I mean, if you have this geometric locality constraint, then obviously you have to satisfy the Brevy-Paulin Terhal bond. But to achieve a particular NKND, you need non-local interactions of certain length, and they basically quantified that, which were also they showed that it's asymptotically optimal. So this Samuel Dai. Really. So this was like just last year set, yeah.
But are there codes known that saturate these? Let's say similar to the good LDPC codes, they're good local LDPC codes?
I mean, like, yeah, Tori code.
Maybe in higher dimension, of course, in 2D it wouldn't work, but maybe in 3D or higher dimension.
I mean, Tori code, right? Is such as BPT bound.
Yeah, well, 2D, maybe it's not that good, right? So.
Okay. I don't know. Maybe. So you want this one, right? So let's say this one.
Yeah, they could.
So Tori code, for example, very much satisfied. Right? So let's say k equal to constant and d equal to n, d equal to square root n. That will satisfy. Like this one. But maybe you want for higher d. I don't know. Maybe like higher variants of Tori code. I mean, I think it should be known. Yeah. Yeah, but this is a very strong, like constraint, like coming from geometric locality. So that's why surface codes and so has such a high overhead.
Hello.
Yeah.
Yeah, for the hypergraph product codes, we take two seed codes, right? Parity. So both these seed codes have to be of the same type. Like, let's say both have to be CSS codes.
No. Seed codes are classical, right? So I mean, you are taking classical codes, two classical codes, and you are constructing that to, I mean, using that to construct a CSS code.
Oh yeah. No, even in that case, like those classical codes have to be of the same kind. Like let's say both have to be classical LDPC, or one can be a different parity check.
I mean, it's some parity check matrix, right? I mean, it can be it's H1 and
Okay.
H2, and they can be, you know, they can take it's R1 cross N1, the other is R2 cross N2. Yeah.
Okay, and it so it has only been done for like a product of two parity checks, or more, like H1,
No,
H2, and H3 also.
I think people have developed this. So you can think of it in terms of chain complexes, and basically it's tensor product. So normally you can think of, you know, like a regular classical code as length two chain complex, and
Hmm.
one can take tensor product of two such chain complexes and develop a CSS code which is a length three chain complex. But I can take many
Hmm.
such, you know, like length two chain complexes and develop it, and people I think call that higher dimensional hypergraph product code. Right? Yeah.
Okay,
Where
okay,
by dimension maybe it's like number of tensor product you take. Yeah.
okay,
Like
okay. Thank you.
yeah. So it has been done. It has been done for, you know, like as many
Okay.
tensor products you want. Yeah.
Okay, are there more questions? Okay, I think there's no more questions. So then let's thank Kishor again for the very nice tutorial. And okay, then we see each other next week again on Wednesday, right? Again.